EM wave out of the total area of the antenna. The maximum effective aperture is when the power received is also maximum. So, and then we did show that the maximum effective aperture of a short dipole or a Hertzian dipole is 0.119 lambda square. So we took a electrical circuit. We employed the maximum power transfer theorem where the load impedance is the complex conjugate of the source impedance. Then we found the current flowing. Then we found the power received. After we find the power received, we divided by the maximum power density, sorry, average power density, power received to the average power density. Then you get some equation for a maximum effective aperture. Substitute radiation resistance is equal to 80 pi square dl by lambda whole square. That is the radiation resistance of the short dipole. So you will get the maximum effective aperture as 0.119 lambda square. Okay. So this is what is the effective aperture of a short dipole or Hertzian dipole. So then we did prove that the maximum effective aperture of a lambda by 2 dipole is 0.13 lambda square. So for that we took one electrical circuit. Consider lambda by 2 dipole of length L is equal to lambda by 2. Let the direction of the incident electric field be a taken E theta phi of E cos of 2 pi by lambda into y. Then we found the voltage by considering the area under the curve 0 to lambda by 4. I integrated. While integrating, I substituted E is equal to cos 2 pi by lambda into y. Then you get a value for VOC. Then the same way, power received maximum is V square R by 8 radiation resistance from the previous equation that I have substituted with power received to the average power density. After I substitute, I'll get some value for AM, maximum effective aperture. Then for maximum effective aperture, substitute radiation resistance of half wave dipole as 73 ohms. When you substitute that, you will get 0.13 lambda square. Then we also found the relationship between directivity and maximum effective aperture. Directivity is 4 pi by lambda AEM. That is the maximum effective aperture. In this case, maximum effective aperture is 0.13 lambda square. So directivity will be this. In case of short dipole, it is 0.119 lambda square. So substitute accordingly and you will get the value. So we will show that the radiation resistance of lambda by 2 dipole is 73 ohms and that of short dipoles is 80 pi square dl square by lambda square in the 4th module. That is what I had taught in the previous class. Is it clear? My dear friends, is it clear?
Yes, sir.
Yes, sir.
Okay. I hope whoever attended the class attentively understood what I am trying to tell you. And you can also have a group discussion. You can have a small groups. Already you have made a project group. So why don't you utilize those project groups for learning your courses also together? Joint learning as a very good thing. Since we are not meeting in the class, I am not seeing you physically, and we are only meeting through this online mode. A group of four discussing things will be make it much easier. Okay, today we'll go into topic known as a radio communication link, also known as your Friis transmission formula. Write down if you have a notebook.
Yeah.
Please
Excuse
write
me.
down. Yes, ma'am.
The screen isn't shared, sir.
Thanks for your. Okay. Can you see the screen now?
Visible, sir.
sir.
Is it visible?
Yes, sir. Now it is visible.
Yes, sir.
Okay. So today we'll be reading what is known as the Friis transmission formula. FR Friis transmission formula. Okay. Friis transmission formula. This is also known as your radio communication link. Okay, so please draw one structure. This is your transmitting antenna. This is your receiving antenna. Yeah. So this is the effective aperture of your transmitting antenna. This is the effective aperture of your receiving antenna. This is the distance d of separation between your transmission and the receiving antenna. Okay. Now just write down the Spritz transmission formula on the radio communication link was developed by Professor H.T. Friis of Bell Telephone Laboratory in the year 1946. Okay, this formula is useful in obtaining the power received by the receiver, and this Friis transmission formula is based on the concept of effective aperture. Okay. Write down. Now consider a radio link between the transmitter and the receiver as shown in the figure. Are everybody able to see?
Yes, sir.
Okay. Let D, that is distance in meters, be the separation, between the two antennas. Okay. Let ET be equal to power radiated by the transmitting antenna PR is equal to power received by the receiving antenna as per Friis transmission formula. Power radiated is equal to PT divided by 4 pi d square. This is equal to equation 1. Okay, continue. Assuming that the power radiated is equal to power transmitted, assuming 1 second, I'll just interrupt here. The Spritz transmission formula is an empirical formula. Empirical formula means it doesn't have a proper derivation, unlike your other antenna, this one. So this is an empirical formula. So whenever you have a empirical formula, there are a lot of assumptions which are made. So when there are a lot of assumptions which are made, so one of the assumptions which is made by assuming power radiated is equal to power transmitted. That means, what is the difference between transmitted power and radiated power? Anyone? Anyone? What is the difference?
Radiated power means, I think, something which comes out of the modulator. I mean, it's not yet out of the antenna, but radiated power is something which is wirelessly transmitted in the medium.
No. Power radiated means the power which is actually coming from the antenna, just
Yeah.
out of the antenna. That is your radiated power. The transmitted power and the radiated power, there may be a small error depending upon so many other minor losses which we are ignoring. Okay, so so this is the difference between your power radiated and your power transmitted. So in your power radiated, actually that is the radiated power from the antenna. So but your transmitted power from the antenna can be minorly different from the power radiated from the antenna. So it will be a slight difference. So this is what is the difference between the power radiated and the power transmitted. Anyone? Sorry, the microphone got switched off. Any other doubts? Anyone? Can you hear me now?
Yes, sir. We can.
Yes, sir. No doubt, sir.
Okay. Okay. Fine. Write down. If GT is the, can you see my screen?
Yes,
Yes,
sir. We
sir.
can.
Okay. If GT is the directional gain of the transmitting antenna, if GT is the directional gain of the transmitting antenna, when the power density produced at the distance d by the transmitting antenna is given by PED, that is your power density at a distance d is equal to gain of the transmitting antenna into power transmitted by the transmitting antenna divided by 4 pi d square. This power transmitted divided 4 pi d square is what Friis predicted. Now it has no derivation in that. It is just that he is assuming that this is this. So tomorrow Saurabh has to come up with a formula. Purva Chandra Prakash used to come up with some better formula than what is I have written now. Then it will be Purva Chandra Prakash transmission formula, or Saurabh transmission formula, or Narayan transmission formula, or Mahima transmission formula, or as the case may be, or Anusha transmission formula. I just took out some names. Don't mistake me that I have not taken out all 115 students' name. So just for make the class lively, I told. So you come up with another transmission formula, it will be named after this. See, 1946, this particular gentleman from the Bell Laboratories found this. We are still using. What is the date today? What is the date today?
25th
25th.
September year.
2020.
Which year it was discovered?
1946.
I am absolutely sure Friis will not be alive right now. So still his formula is used. Don't you want your name to be embedded in history like this?
Yes.
You want or you don't want? I'm just asking you a question. Let AER, I'll keep writing, you keep answering, so that the class can be interactive. Tell me, you want your name to be embedded in the scientific history, yes or no?
Yes, sir.
Who is answering? Saurabh.
Yes, sir.
Okay. Purva Chandra Prakash, you want your name to be embedded in the scientific history?
Yes, sir.
Okay. See, I'm just telling you 1946, this is 2020, almost what, 50, 60, 74 years back he has discovered. Still we are remembering Friis, and you are writing this, and it may be asked in the VQ exam, you may write this, you may end up getting some marks. Whom you have to thank? Whom you have to thank? I'm asking you whom you have to thank if you get the marks.
Friis and you, sir.
Huh?
Professor H.P. Friis and you, sir.
No, you have to thank the Friis. He is the person who discovered this. I did not discover. I'm just telling you what he did. So I'm just a medium of instruction. So you need not thank me. You have to thank whom? Friis. Okay,
Yes, sir.
not me. So if you get some good marks out of this, if you get some good knowledge, finally you end up joining NASA and doing something, whom you have to thank?
Friis, sir.
Not me. See, I am a very ordinary person trying to motivate you to do something extraordinary. That is the only thing. Okay. So if you want to know more about antennas and all, see, actually my research area is electromagnetic waves and photonics. Okay. This antenna is our offshoot of it. I'm just teaching you. So if anybody having any doubts, or you want to really do research in antenna, or you want to do some extraordinary work, you are really interested in doing some extraordinary projects in antenna, please contact Professor KJ Vinay from Indian Institute of Science. He is like a Bible of antenna for us at IASC. Professor KJ Vinay from Indian Institute of Science, Department of ECE. So he's a very friendly person. He'll be very approachable. So if you really have an excellent idea, we want to implement this, or you want anything to be given more insight, you can always approach him. Don't tell that I don't know anything on antenna, please teach me antenna. So this is not the way. So when you are approaching such professors, you should have something concrete with you. Then if you want higher help, you can always ask them. Okay, so that is about some talking. So if GT is the directional gain of the transmitting antenna, the power density produced at the antenna at a distance d by the transmitting antenna is given by PD is equal to power density at the distance d given by gain of the transmitting antenna into power of the transmitting antenna divided by 4 pi d square watts per meter square. Let AER be the effective aperture of the receiving antenna. The power received by the receiving antenna is now modified as E of R, power received at the receiving antenna, is equal to power of the transmitting antenna divided by 4 pi d square into gain of the transmitting antenna into effective aperture of the receiving antenna. This much in watts. This is in watts. All this is equation 3. Directive gain can also be expressed in terms of the effective aperture of the transmitting antenna as gain of the transmitting antenna is equal to 4 pi into effective aperture of the transmitting antenna divided by lambda square. Call this as equation number 4. Substitute equation 4. Substitute equation 4 in equation 3. So your gain what will become is, so if you instead of GT substitute 4 pi ET divided by lambda square. Okay. So what you get? So shall we substitute? Okay. So what you end up getting? Power received is equal to power transmitted divided by 4 pi d square into gain of the transmitting antenna, that is 4 pi into effective aperture of the transmitting antenna. Okay, effective aperture of the transmitting antenna divided by lambda square into effective aperture of your receiving antenna. So your 4 pi will get cancelled. So what you will end up getting is power received is equal to power of the transmitting antenna, effective aperture of the transmitting antenna, effective aperture of the receiving antenna divided by d square lambda square. So this is what your Friis transmission formula tells. This is your final derivation. So in your VTU exam, they will ask state and prove Friis transmission formula. So what we have done, I'll just go through based on the concept of effective aperture. We are doing Friis transmission formula. Let P of T be the effect power. Let okay, sorry. Let P of T is the power radiated by the transmitting antenna. P of R is the power received by the receiving antenna. As per Friis transmission formula, power radiated is equal to power transmitted divided by 4 pi d square. Assuming power radiated is equal to power transmitted, and if GT is the gain or the directional gain of the transmitting antenna, then power density produced at the distance d by the transmitting antenna is equal to power density at the distance d is equal to gain of the transmitting antenna into power transmitted divided by 4 pi d square and watts per meter square. Let AER be the effective aperture of the receiving antenna. The power received by the receiving antenna is given by PR is equal to PT divided by 4 pi d square into gain of the transmitting antenna into effective aperture of the receiving antenna. Directive gain can also be expressed in terms of effective aperture of the transmitting antenna, as gain of the transmitting antenna is equal to 4 pi AET effective aperture of the transmitting antenna by square of the wavelength. Substituting equation 3 in equation 4. Equation 4 in equation 3, we get power received is equal to power transmitted into effective aperture of the transmitting antenna, effective aperture of the receiving antenna divided by square of the wavelength and the square of the wavelength and distance. Any doubts?
No, sir.
Okay. Let us do one problem on Friis transmission formula. Anusha, KR, any doubts?
No doubt, sir.
Okay. What is the maximum power received? All you people enjoying antenna class, or is it very boring? So I can't
We are
change the
enjoying,
syllabus.
sir.
Pardon, ma?
We are enjoying the class, sir.
Okay, thank you. No, see, I can't change the syllabus which is given by the university. I can only dissipate what is given in the university to so that you can write the university exam well. I'm trying my level best to make it as interesting and as communicative as possible. If you people have better ideas to make it more communicative or make it more jovial, I'm welcome for suggestions. That's why I'm trying to tell you about Friis and trying to motivate you to become like Friis. Okay, so what is the maximum power received at a distance of 0.5 kilometers over a free space of 1 gigahertz okay, 1 gigahertz circuit. Consider transmitting antenna. Consider transmitting antenna with 25 dB gain and receiving antenna with 20 dB gain okay. This gain is with respect to lossless isotropic source, the transmitting antenna input, the transmitting antenna input is 150 watts. So I'll repeat, what is the maximum power received at a distance of 0.5 kilometer over a free space of 1 gigahertz circuit? Consider transmitting antenna with a 25 dB gain and a receiving antenna with 20 dB gain. The gain is with respect to lossless isotropic source. The transmitting antenna input is 150 watts. The transmitting antenna input is 150 watts. Okay. Okay. So, fine. How do we do this problem? Any idea? You are all to be engineers. Come up with a solution. How do we do this problem? Okay, Saurabh, but please tell me.
So the formula in order to find the maximum power received is PT into AET into AER, the effective aperture of the receiving antenna,
Yes, sir. Okay.
divided by the lambda square, that is the wavelength, and multiplied by R square.
Okay.
So we have to
Instead,
find.
one second. See, I'll just go back to your previous class. Okay. This is the directivity and effective aperture. 4 pi by lambda square into effective aperture is equal to directivity. Please write down this formula. No, directivity is equal to 4 pi by lambda square into effective aperture. Please write down this formula. So what will be your effective aperture? What will be your effective aperture? D into lambda square by 4 pi. Got it?
Yes, sir.
All of you got it?
Yes, sir.
Got it?
Yes, sir.
Okay.
Yes, sir.
Okay. Very good.
Sir.
So, yes, ma. See, I'm doing it very slowly since we are doing it online. See, I can't simply run through the things for completion of syllabus. Okay, what is the wavelength? C by F. So, what is C now? Sorry, C is your speed of light. 3 into 10 power 8
Meter per
meters per second divided by 1 gigahertz. That is 1 into 10 power 9. How much you get the wavelength?
0.3 meters.
0.3, sir.
Okay, 0.3 meters. So this is approximately actually your length of the antenna. Whatever is your lambda. So if it is a lambda by 2 dipole, what will be the length? One small question. If it is a lambda by 2, lambda is 0.3. What will be lambda by 2 length?
0.15.
As simple as that. Okay. So what is the gain of the transmitting antenna? Directive gain of the transmitting antenna? G of T?
25 dB.
25 dB. Okay. So assuming this is the maximum directive, okay, gain is 25 dB. This can be equal to directivity, assuming it is the maximum directive gain. What is the gain of the receiving antenna?
20 dB.
20 dB.
20 dB. So assuming this is the maximum directive gain and there is no loss, this is the directive gain. This is your gain. This is the maximum directive gain. So D of T is nothing but equal to DT max. This is equal to your GR max. So what is your effective aperture of the transmitting antenna in terms of this one? That will be 4 pi by, just now we saw 4 pi by lambda square, 4 pi by lambda square into what? Gain of the transmitting antenna. Okay, gain, or in this case the directive gain of the transmitting antenna d of t. So what will be your correct? So sorry, I did exact uta here. So directivity is this one. Sorry. Okay, rewrite this. What is your directivity? Directivity of the transmitting antenna 4 pi by lambda square into effective aperture of the transmitting antenna. So what will be your effective aperture of the transmitting antenna? No? Directivity of the transmitting antenna into lambda square divided by 4 pi. Similarly, effective aperture of the receiving antenna EER will be equal to DER lambda square by 4 pi. Is it clear? All of you, is it clear?
Yes, sir.
Yes or no?
Yes, sir.
Okay. So what is your power radiated? Your Friis transmission formula. Please tell me power transmitted into effective aperture of the transmitting antenna into effective aperture of the receiving antenna divided by lambda square d square. Am I right? Am I right?
Yes, sir.
Yes, sir.
Okay. What is the input power? What is the power radiated given? Antenna input is 150 watts. So assuming power input is equal to power radiated is equal to power transmitted. Assume input power is equal to radiated power is equal to transmitted power. So what I should write here? That is equal to here 150 watts. Is it clear?
Yes, sir.
Yes, sir.
So what I should write here? Power transmitted is 150. What is the effective aperture of the transmitting antenna in terms of directive gain? DET. DET. Okay. So what will happen here? Lambda square is there. Okay. DET lambda square into DER lambda square divided by lambda square d square. This will be here 4 pi 4 pi. So this will be 4 pi 2 times 4 pi. 4 pi into 4 pi. I'm simply substituting here. All of you got it what I'm trying to do? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
The effective aperture of the transmitting antenna, effective aperture of the receiving antenna, I'm substituting in this equation. AET, that is equal to directive gain lambda square. This will be directive gain lambda square divided by 4 pi 4 pi. That 4 pi 4 pi I'm writing here. So 1 lambda square will get cancelled with this 1 lambda square. So what I will end up getting is 150. Okay. So okay, this is in dB. Please convert back into some numerical value. This is gain is in dB. I forgot to do it. 25 dB is how much back? Do anti-log.
316.22, sir.
316.22.
22.
Okay, 316.2. This one, do anti-log.
100, sir.
Excellent. Okay. So while substituting the numerical value, convert into this because later you can convert into because it is in watts. So what will be? This will be 316 what into 100, what is your wavelength? 0.3 square. Got it, all of you?
Yes, sir.
Divided by, what is your distance? I forgot the distance now.
0.5 kilometers.
0.5 kilometer. 0.5 kilometer in meters will be how much? D is equal to your 0.5 kilometer. 0.5 kilometer is how much in distance? Into 1000, 500
500 meters.
meters. Okay, so I'll rewrite this as 4 pi square into 500 square. This is your power received, P of R. Please find out how much it is.
10.7 milliwatts, sir.
10 point.
7 milliwatts.
Is it 7 or 10.8?
Sir, I got 10.7.
Okay, we will go with what Saurabh has got. This is the power received. What is the input power? This is the answer.
150 watts.
Huh?
150 watts, sir. Power transmitted.
So your power transmitted, that is equal to 150 watts. What is your power received? 10.7 milliwatts. What is the distance? 500 meters.
500 meters.
So what it signifies is if you are using a lambda by 2 dipole antenna. So why he has not told which antenna you are receiving actually you are using. He is telling a lossless isotropic source. That means it is radiating equally in all directions. Suppose you are using a lambda by 2 dipole antenna. So what will be the lambda by 2 dipole antenna length? 0.3 by 2. That is equal to 0.15 meters. So if you are using assume you are using 1 point, lambda by 2, that is your general antenna, 0.15 meters length. You are transmitting or radiating 150 watts of power using this antenna over a period of half a kilometer. So how much you are receiving power? 10.7 milliwatts. So what is the transmitted power? 150 watts. So what is the receiving power?
10.7 milliwatt.
So from watts it has gone to milliwatts. So when you are at a very long distance, the signal will deteriorate very sharply. Now what is the only way I can increase this? Suppose wavelength is 0.6. What happens here? If lambda is 0.6, can you tell me what will be the power received? Here you substitute 0.6. What happens to the received power?
43.2 milliwatts.
Huh?
43.22 milliwatts, sir.
So as you increase the length of the antenna, your power received. So suppose your lambda is 0.6 meters. So what happens to the received power? 40.
43.22
How much?
milliwatts.
43.22 milliwatts. See, the crux of the story is if the wavelength or the length of the antenna increases, your power received also increases. And it is quite a big increase. Suppose you make the length as 0.9 meters now. Now make the wavelength as 0.9. Tell me what is the power received?
97.25 milliwatt.
What you get, bar?
97.25 milliwatts, sir.
So what is the summon substance? What you learn from this? What you learn?
We
As
observe-
wavelength increases, the power transmitted also, power radiated also increases.
Power radiated.
No, sir, power received.
Suppose I am the transmitting antenna. You people are at Rajan Kunte. If I am transmitting with higher length of the antenna, your power received will also increase. So this is the what I wish to tell here. Suppose you want to send your signal to outer space, what happens? What happens?
Very huge antenna.
What you will get, picowatt or nanowatt of power? That is the what is the next question we are going to do. Shall I stop here or you want me to do one more question? You need a break, I hope so.